Right. So we need to set up a midterm schedule. It seems we need to cover 8 more lectures to prepare for your midterm exam, and I think we are on the right track. So we have more than 4 weeks from today, so I guess we can take the midterm exam on schedule. So let's schedule our midterm exam on 22, Wednesday. Okay. And since we have a larger number of students, I think we need to split this class into 2 groups, and each group will take exams in different classrooms. I will announce about the location later in iCampus. So last time I introduced what is correlation variable. Basically, this correlation variable means a variable which references a record that is used in outer query. So in this particular example, this nested query inside the where clause is using variable s. But if you look at this select query, you cannot find what is s. This variable is a correlation variable, and this variable references a record, a single record of outer table. And it seems I failed to explain this complicated query last time, so I prepared some more slides today. So this query is about finding all students who have taken all courses offered in computer science department. In the previous older lecture slide, it was biology, but I just changed it to CS. So let's assume that we have these 2 students named Alice and Bob, and we have course information and which courses were taken by which student in table. So if you look at this course table, we have 3 computer science courses: database, operating system, and multi-core computing. And our goal is to find the students who have taken more than these 3, who have taken all these 3 courses. So let's assume Alice has taken 3003, which is, database, and 3004 operating system course, but she didn't take multi-core computing. She instead took biology 101. Okay. So Alice took just the 2 courses. So the courses taken by Alice is not a superset of computer science courses. Okay. So what we want to find is we want to find the students who have taken courses that is a superset of all computer science courses. Okay. So if you look at Bob, Bob took those 3 computer science courses, and additionally, Bob also took a biology course. So here, this yellow colored ellipsis represents all computer science courses, and Bob took all these 3 courses, and additionally, he took biology 102. But Alice took only 3003 and 3004, but she didn't take 3021. Instead, she took biology 101. So those courses taken by Alice is not a superset of computer science courses. By checking this superset and subset condition, we can find, we can check if a record includes, a student record took all the courses offered by a particular department. So this is the query that you saw in the previous lecture. Here we have 2 nested queries. The first query doesn't use correlation variable. If a nested query doesn't have correlation variable, DBMS will simply evaluate this query and store that output table in main memory or disks, and we call those intermediate output materialized table. So what is this query? This query finds course IDs from Department Computer Science. So if you look at this course table, these 3 courses satisfy this condition. So their course IDs are materialized in storage or memory. Okay, after evaluating this first nested query, we should check the second nested query. But here we have a correlation variable S. How do we evaluate this? It works exactly in the same way with how we process this nested for loop. So S references a student record, student table, and let's suppose S is currently referencing the first record of a student table, and this right table. After we materialize the output for the first nested query, we don't need to access course table because course table is not used in the outer query, or it is not used in the second nested query. So I just removed it from the slide for simplicity, and I draw this materialized table for the first nested query right here. And then let's process this second nested query using correlation variable S. So S is referencing Alice, whose ID is 20. And we scan text table. We access this text table. Oh, there should be S here. Text table, and check this condition. S's ID must be equal to the current table. T is an alias of the text table. So S's ID should be equal to text table's ID. So we compare whether the first record of text is equal to Alice's ID 20. It is. So this will be selected. Each course ID, SW3003, will be selected, and we move on to the next record. Again, the second record also has a 20, so this second course ID, 3004, will be also selected, and Biology 101 will be also selected. But the rest of the 4 records do not satisfy this predicate, so only these 3 records will be selected for Alice. Okay? And we process except operation. This is a set difference operation. So we subtract these records, courses taken by Alice, from the materialized table, which is the computer science courses. And here, since this right operand is missing 3021, the output table will not be empty. And therefore, this not exist operator will return false value. So this whole predicate for Alice is false. So Alice's ID and name will not be selected in this entire query. Okay? Then we move the correlation variable to the next record, and now we compare take table's ID with Bob's ID 30, and these 4 records will be selected, and we deducted those 4 records course ID from the materialized table, computer science courses. And since this right operand, which is the course ID is taken by Bob, is the superset of computer science courses, the output will be an empty table. And since this is empty, not exist operator is going to return. Give me 1 second. Yeah. Since it's empty, not exist returns true. I was confused. Yeah, when I speak in English, half of my brain is half of my brain is processing this language. So, yeah. Anyway, so that's it. Any question about this correlation variable? No? Good. All right. Next. What is this? This slide is for unique operator. Okay. Again, we are using correlation variable. I should have prepared another detailed step-by-step slide for this. let's just use my pen here. We want to find all courses that were offered at most once in 2009 and 2009. So if a particular course was offered more than once, I mean let's say twice, then the same course ID can be returned twice. So this unique operator is used to check if all records of the right operand table is unique or not. If there's any duplicate, this unique operator is going to return false. If every record has unique ID, I mean unique record, then this unique operator is going to return true value. So here, let's process this n most once condition at the end. And we want to first find out course IDs offered in 2009. So we should check section table, which contains section ID, year, and semester information, and we rename the section table as R, and each year must be 2009, and we'll select course IDs. Okay. But there is going to just list a bunch of course IDs that were offered in 2009. How can you check if those, if that intermediate table give me 1 second. Why do we need this correlation variable here? So if you ignore this correlation variable condition, the output table, the materialized table, will have bunch of course IDs like 3003. Let's say this was offered in fall and spring as well, then it will be selected twice because these two courses offered in different semesters. Okay, let's suppose we got this output table, and how can you check if they are, if each records are unique or not? How can you check if there can be some other courses like ECE 101, Bio 101. We want to check each record. We want to check record by record. So this could be the output table when we don't have this correlation variable, and when you have mixed records, mixed course IDs like this, then it will be very difficult to write. It will be very difficult to check this n most once condition. So what we do here is, using correlation variable, we access course table. So inside the course table, it is guaranteed that course IDs appear only once. SW3003 will appear only once, and ECE 101 will appear only once. Bio 101 will also appear once. So the correlation variable T will reference a single record of the course table, and then we now access the section table. Section table contains the actual course offering information, and so here we have a section table, and let's suppose SW3003 was offered in spring 29 and also fall 2009, and ECE was offered only once in 2009. Let's say biology also was offered once in 2009, like this. Then we reference a single record of the course table, and we scan this whole table and check if the course ID of section table matches this correlation variable T. So EC 101, biology 101, they do not match with this course table's correlation variable T, so these two records will be ignored. And then since this matches the course table's ID, and this second record of section table also matches the course ID of the outer table, and also the year condition satisfied, it is also satisfied. So these two records will be selected for the first record of the course table. Okay? Oops. So these two records will be selected. Now we can execute this unique operator to check if all records of this intermediate table has unique values. It is not unique. We have the same data twice. So this unique operator is going to return false for the correlation variable T. So we move on without inserting any output in the table, final output table. And we move on to the second record of course table EC 101, and we scan this section table again, and we find a single record. So for this second correlation variable T, and this nested query is going to insert just one single record. Since this is a unique value, unique operator is going to return true for the second record of the course table. So EC 101 will be selected. Similarly, Bio 101 will be also selected. Okay? Question?
Can be theoretically implemented using count, right?
Using counter.
So we just count the output of this second table instead of using
Yeah, I guess you can do that. Inside where clause, you run nested query that count the number of records, and then run another select query using count operator and deduct those two numbers. And if they are equal, the whole where predict will be true. Yeah, you can use such logic. But I don't think that will be much more simpler than this one. It will be similar.
One question about this unique operator. So it compares like the whole tuple, right? So what if, for example, in a subquery we would have not just
Multiple.
but we would also have like the fall, spring.
Yeah, if it has multiple attributes, then it checks all those attributes, and only when all attributes have the same values, then it will return true. Good question. Okay, let's move on. This nested query can be used in from clause as well. What is this? Let's not look at this description. Let's just interpret this query. Let's look at let's look at nested query first. We access the instructor table, and then we sort the instructor table using department name and group those records with the same department name, and then apply this aggregate function. So this nested query basically calculate the average salary of each department. Like computer science is making average 1,000, electrical engineering is making 2,000, something like that. And then we use this output table of this nested query for outer query. Okay, this is going to be the table that we use in this outer query. we call this materialized view and materialized table. Intermediate table and materialized table, they are the same thing. And from this materialized table, we check the average salary. This second column is the average salary. If it is greater than this number, 42,000, the where predicate will be evaluated true, and each department name and average salary will be returned. And this same query can be written it's almost the same. But they are the same. They are the same. They, I mean, they differ in terms of renaming scheme here. So this upper query is renaming the output of this aggregate function. So it is renaming only single attribute, and this lower query is giving a name to that materialized table. So this upper query generated this intermediate table. This table doesn't have any name. If you want to use that table in the outer query, it is better to have a name. So you can give a name using edge operator like this. So this select query will return anonymous table, and by using edge operator, you are giving a name to the table, and attribute names can be followed inside the parentheses. Question?
참고로 재밌네요. 제가 했을 때 그 위에 것처럼 하면 에러가 나던데 프롬에다가 저런 네스티드 코드를 사용할 때 항상 별칭을 지정해줘야 된다.
In Postgres?
네.
Oh, really? So his question is, he tried this query. In Postgres, he got an error since this intermediate table doesn't have a name. And it seems Postgres requires to give a name to those materialized views if those materialized views are used in the from clause. But I don't think that is a part of SQL standard. Our textbook, I mean, this example is from our textbook, and our textbook is written based on this SQL standard. So every DBMS has a slightly different behavior. So I don't know. Oracle is the most compatible with the SQL standard. So if you try this query in Oracle, I guess it's going to work. Maybe, I don't know. Anyway, thanks for bringing up that issue. Next, with clause. Sometimes queries can be really long and complicated. In that case, you can start your query after defining view, defining an intermediate table. So what I'm saying is, look at this query. I don't think this is a complicated query, but I think this query is just showing how to use this with clause. So let's suppose you have a really long query. You have a select from and where, and you use nested query inside the from clause, and the same nested query is needed in the where clause, and maybe you need the same nested query in multiple places in the where clause. And this kind of complicated queries can be used, although it is not recommended. In that case, instead of writing the same queries, same nested queries here and there, it is better to define. And to give a name to that nested query. You can do that using with clause. So when you have a with clause, we call this view. we call this view name. You need a view name and attribute names for that view. View is like a table, but it is not a physical table. It is just logical view, a logical table. So view name followed by view's attribute, and then as keyword needs to be followed, and then you define the nested query. Once you define this view, this view name can be used in the following query as if it is a normal regular table. Okay, this is like macro in C language. You define a variable or I mean symbol or function in C language, right? Just like that, in SQL you can define a complicated query using with clause. That's the purpose of with. So with clause is very useful for writing long and complicated queries. So let's write this query using with clause. We want to find all departments where the total salary department total salary is greater than the average of the total salary at all departments. We need to calculate the average of the total salary. So we need to first calculate the total salary of each department. So here, using group by clause, we create a table that contains each department name and each department total salary. And we gave a name to this table. Depth total is the name of this query. And you can define another view after a comma. If you want to define, let's say, 10 views, then you will need to write 10 queries separated by a comma in between. And the next view is named depth total average. And this depth total average is using the view you just created above. So depth total is defined right here, and that is used in the next view. And what we do here is we just calculate the average of the total salary of each department. Okay. After defining these two imaginary table, virtual table or view, you can write those names as if they are regular tables. Question?
With view, you said that it is like macro, and when we use that view multiple times, is the view will calculate it multiple times or just once and instead in memory?
That is a really good question. So it works exactly like a macro. So here inside this actual query, we have this view name depth total. When this query is given to DBMS parser, the language processor, parser is going to replace this string with the definition of this view. So if this depth total is used in multiple places, then the same query will appear multiple times in DBMS. I mean multiple times in the translated query. That is how it is processed at the first place. But even if that complicated long SQL query is given to DBMS, DBMS is going to translate it into relational algebra operations and then perform optimization. It is going to optimize the query to reduce the complexity of query evaluation plan, and it will choose the optimal, it will choose the most efficient query plan that it can find and run it. So even if this query is expanded multiple times, in the translated query, they may be, these operators may be applied only once, but it is not guaranteed.
In that view, we use instructor table. When we make this view and 그 다음에 그러니까 이거 텍스트 파일이라는 뷰를 저희가 인스트럭터 테이블을 통해 만들었잖아요. 이거를 이렇게 만든 다음에 인스트럭터 테이블 날려버리면 그거
I think I have a slide for your question. So please hold your question. I will get to that slide very soon. So his question is, what if we make this view and then this delete instructor table? What happens? And I have a separate lecture slide for that issue. So it depends on. I mean, the answer depends. I'll explain that issues later. Any other question? No? Okay, let's move on. Next, Scala subquery. Sometimes SQL query may return a single value. Like if you run select the query with count star, it is going to return just a number. And we call this Scala subquery. I mean Scala query. If a Scala query is used as a nested query, then of course it is called a Scala subquery. And the Scala subquery can be used for comparison operators. So if you look at this second query, we use this comparison operator with this Scala query. But at first glance, this query doesn't look like it returns a single value. It may return multiple values, right? If it returns multiple values, then this query will fail. But if this query, nested query, returns a single value, then this whole query will succeed. Okay? So when you use this nested query with comparison operator, like a greater than, less than, or equal to, then you must make sure that your nested query returns just one single value. And here you see that this nested query is used in select clause. This is also possible. This is also possible. And here it seems this department is also correlation variable, because the current table doesn't access department, right? Next, we are almost done. So far we learned how to process, how to write read queries. But DBMS allows us to modify data. So deletion, insertion, update, these operations are also allowed. And let's see how we can do that. For deletion, we use delete from clause, delete from and table. You cannot delete a specific specific attribute. You should delete row by row. Therefore, unlike select operator, delete operator doesn't allow us to specify attribute names. But we can give a condition for deletion. If you run this query, DBMS will check department name attribute, and only if its value is finance, the particular record will be deleted. All other instructors, like from computer science or electrical engineering, they will stay. Only instructors from finance department will be deleted by this query. What is this query? Let's just read this SQL. We need to parse we need to look at inner query, nested query first. We access the department table and check if the building is Watson, and those department name will be selected. So we selected department named that is located in Watson building, and then we use in operator. What is in? It is a set membership operator. Now we check instructor table, and if the instructor's department name is included in this right operand set, which is those departments that are located in Watson building. So we will delete instructors that work for the departments located in Watson building. That's what this query is doing. And nested query can be used also for delete from, update. Can you use nested query for insertion? No, I don't think so. But for deletion and update, we can use nested query like this. And this is Scala query. You select average salary and compare the salary, average salary with each instructor's salary. But let's look a little more careful. I mean, how should I say? Let's look at this query a little more carefully. Here, we are deleting instructors, and here we are calculating average of instructor's salary. Oh, what should we do? Let's suppose instructor 1, 2, 3 are stored in a table, and their salaries are like 1,000, 2,000, and 3,000. So initially, when you run this nested query, it's going to return 2,000. Okay? Do we have a correlation variable? No. So this will be materialized and used for subsequent query processing. And then now we should scan instructor table once again and check if the first instructor's salary is less than 2,000. True? So this guy will be deleted from instructor. Should we re-evaluate this average operation? No, we don't. Unless correlation variable is used, nested query is evaluated only once. So we keep this number in main memory and use this number for all delete operations. Okay? It might be confusing, but there is how DBMS process this. Question? No? Good. Next, insert operation. For insertion, we need insert into clause, insert into a table name, and value. We can use nested query for insertion as well. I think I have an example in later slides. Anyway, if you want to insert a single particular record into a table, you use values clause. So you specify value of each attribute. Let's suppose course table has course ID as the first attribute, title as the second attribute, department name as the third attribute, credit as the last attribute. Suppose you remember the order of these attributes, and then you can just put values like this. But sometimes you might be confused. Oh, is it course ID the first attribute or second attribute? I don't remember. In that case, you can specify attribute names after the table name, and these ordering can be changed. Maybe if you could be confused. I mean, suppose you are confused and you thought that title is the first attribute of a course table, so you put title and course ID as the second attribute. You can do that as long as you change the order of these values. Since you specify the title is the first attribute, you should give title of the new course as the first value. Okay, so these attribute names and values should be ordered in the corresponding. I mean, they should be ordered in a proper way. But when you specify these attribute names, the ordering of attributes do not matter. Next, sometimes when you insert a record into a table, you might not be sure about a specific attribute value. Then you can store null value in the column. Then you can use null keyword in values clause. Next.
When you change the order with these values, then when it comes to the table, it will be saved with this order or
No, DBMS will reorder those attributes in a correct way. I mean, in the same way with how the table is defined. Next. What is this? Oh yeah, here. This is how we use nested query in insert statement. This select statement is going to return multiple records. Then all records selected by this nested query will be inserted into the table. And again, this nested query select from where will be evaluated fully before any of that output tables records records are inserted into this outer relation. So basically what it means is you can do that. If you want to duplicate all records of a particular table 1, you can run this query. Insert into table 1, select a star from table 1. This nested query will be evaluated first. So let's suppose table 1 contains 100 records. Then 100 records will be stored in main memory. And then we process insert into statement, and those 100 records will be stored into table 1. Okay. This will duplicate every record. Okay. Otherwise, it is going to run infinitely. Whenever you insert a new record, they should be inserted again and again. Next is update operator. Update, set, they are used together. So when you want to update the instructor table, you should put the table name after update clause. And then set clause requires assignment operator. So salary column should be set to this expression. So what it does is it checks salary of instructors, and if a record salary is greater than 100,000, we multiply this number and store that updated number in the same salary column. So what does this query do? It increases the salary of instructors by 3% if they are making more than 100,000. Next, what is this? This is the same query, but this time we check if the salary is less than or equal to 100,000. If they are making, if they are not making more than 100,000, we want to give a 5% increase. That's the meaning of this query. Okay. So if you process this query in this order, we don't have a problem. But what if we process this query in the opposite order? So your intention was to give raise. We want to give more increase for those who are making lower than 100,000. But if you process these two queries in the reversed order, some instructors may get salary increase twice. Let's say one guy was making just 99. Oh no, that's too much. 99,999. Let's suppose someone was making this money. Then when you process this query first, he's going to get 5% raise. That is going to make him on like 4. I don't know. Yeah, 4. He's going to make this money, and then we process this upper query. Oh, since this number satisfies this condition, he's going to get another 3% increase. That's a problem. To solve that problem, people introduced case statement. This works just like a switch case in high-level programming language. So what it does is, after set, we need assignment operator, and we need a case. Case ends with end, and inside the case we have when and then or else. So we check this predicate specified after when clause. If this predicate is true, we execute next statement. I mean, we evaluate this following expression and use that value to update salary column. And then we jump out of this case and block, just like a switch case. If this condition is false, then we enter else block and use the second expression to update the salary. Another correlation. I need coffee. Okay. For correlation, let's first ignore this part. What does this do? We perform natural join for text table and course table. So we are checking which student has taken which courses, and we check whether those students got F grade or not. If it is not F, this is not equal operator. If it is not F, and if the grade is not null, which means grade is known, grade is ABCD, then we we perform some operation. We sum their credit with their credit. Okay. So without this correlation, this inner query is going to add up all the credit of all students who didn't fail in any courses. Okay. With this correlation variable, as we process each student. So in the student table, let's say we have Alice and Bob. Then we don't care about Bob. We only check Alice first, and we access text table using Alice's ID, and we only care about Alice's letter grade. And if Alice didn't get F, and if Alice didn't, if Alice's grade is known, then we add up her credit, and then store her total credit in an attribute named total credit. Okay, this is how we can. This is how we can use this nested query for update operation. And so if you look at this logic, we ignored F grade and we ignored the grades whose value is null. Sometimes it is possible that a student took some courses but their grades are not known. In that case, we want to store null value in total credit attribute. How can you do that? Again, we should use case condition. So after running this, give me 1 second. The case can be used in this following case statement can be used in select clause right here. So we process this natural join and check this correlation condition and letter grade conditions, and then we check if the credit sum of credit is null or not. If it is a number, then we will use that number. If this is null, then instead of storing null, we want to store 0 in total credit. That's yep. Any question up to this slide? Question?
Previous slide, can we use else statement?
Else if? Else when, I guess you mean. Huh? Yeah.
Another
Mm.
cases.
I haven't tried, but I guess we can. I mean, it is supported. It should be supported, right? If not, then we will have too many nested case blocks that is going to make the query very complicated. So I haven't tried it. It should be supported. Maybe you should try in our Postgres. Okay. Finally, we can move on to the next slide. All right. So this is chapter 4, and we will learn some variations of join operations. So what we learned so far is called natural join operation. What? Natural join operation, and we have two more join types. So what is natural join? At this point you should be familiar with what is natural join. When we have natural join operator, we compare attribute names of the two tables and find the common attributes and use that common attributes as join condition. That's natural join. So when these two tables are given, and when you perform this natural join, you will get this output. Only the common attributes will be joined. I mean, how should I say? Only the common attributes will be compared, and matching records will be concatenated. Let's move on. Now, this is not natural join. We perform Cartesian product first, and then compare instructor's ID column against teacher's ID column, and unmatching concatenation will be eliminated. And then we perform projection operation. Although this query doesn't use natural join clause, natural join operator, it works very similar to natural join operation. as you saw last time, when you blindly use natural join operation, unrelated attributes will be used if they have the same name. So you may get incorrect query output. So an example is shown here. We have a student table, text table, course table, and our intention was to join student with the text and then compare ID of student against the text ID. After that, we want to perform another natural join using this intermediate table with the course table. But when you use natural join, the common attribute names will, attributes with the common names will be used, and this might not be what you intended. Then you will get incorrect results. So to avoid that confusion, to avoid that issue, instead of using natural join, you may use using operator. Using operator allows you to specify the attributes that you want to use for join condition. So this example query performed natural join for student table and text table. Since they have only single common attribute, we can safely perform natural join. But when we join the output of this natural join with the course table, there's a department name. There's a common attribute that you do not want to use for the join condition. In that case, instead of using natural join condition, you better use using condition. Using operator. This using operator allows you to specify a particular attribute name that you wanna join. That you wanna use to join. So since you specify the course ID here, we only compare these two attributes rather than department name attribute. Okay. So and there's another variation. Instead of using you may use on operator, on condition. What does on do? It allows you to specify a predicate, just like where clause. Unlike where clause, this on clause can be used only for join operation. So in this example, this on condition compares A against C. A is on the left table, C is on the right table, and when you perform join, you check if T1's A is equal to T2's C. So let's process it like a nested query. We first access the first tuple of T1, then scan these three records and find the matching record that will be inserted into this output table, and then we move on to the next record and we check T2 by scanning the whole record and find the matching record, and that will be inserted into this right table. So it works like a multiplexer, and this multiplexer will use the predicate specified in on condition. Okay, that is how we can use on operator. So this query, given query that is using on condition, on and predicate, is exactly equivalent to the following query that is using where predicate. When you use where predicate, you can put Cartesian product What if we replace this comma with join? Then some records can be removed in the output table, right? And I mean, if you replace the comma with the join, some records might not be concatenated. Even before we process this predicate. So join shouldn't be used. When you use where, comma must be used. But when you use join, on should be used. Why do we need these two different syntax? The main reason is readability. When you read a query like this, you should spend a little bit of time to figure what this is doing. Is it join? Is ID on the student? Is it student ID on project? You need to check the schema and you need to think a little bit to figure out that, oh, this is actually doing the join operation. But if you get this upper query, you can instantly figure out that, oh, this is joining these two tables using ID and student ID. Next, auto join. Consider this case. We are joining table T1 with table T2, and we are comparing attribute A's value with attribute C's value. And let's consider this particular second to the last record of table T1. And if you scan table T2, you will not find number 4 in column C. In regular join operation, this T1 second to the last record will not be included in the output table. But sometimes users may want to include unmatched records in the output table. So even if for this record, this tuple, is not joined with any tuple of T2, you want to store it in the output table. In the case, for those missing attributes, you store null values. This operation is called auto join. Auto join. So we use null value for missing attributes. And this auto join has 3 variations. Left auto join, what you just saw is left auto join. Unmatched records from left table will be inserted. That's left auto join. And let's say we have T1, T2, and unmatched record from table T2 can be inserted in the output table. That is called right auto join. And unmatched record from both tables can be included in the output table. That is called full auto join. I have some examples in the following slides, so you don't have to write down. Let's consider these 2 tables, student and project. And Alice has done on project, has worked for project 1, and Bob, it seems Bob is not participating in any project, and Charlie has done 2 projects. David didn't do any project, and it seems there's another student who is missing in student table who worked on project number 2. Let's suppose we have these 2 tables, and when you run this query, select a star from student, left auto join project, and join condition is specified using on keyword. Then let's start from Alice. oh, Alice matches. So we just concatenate these two records and store it in the output table. And we move on. Oh, Bob is not matched, and Bob is on the left table. So let's store in the output table. But we do not know two attributes of product table. I mean, these third and last columns are from product table, but since Bob's record is missing in product table, we store null values there. Okay, this is called the left outer join. And next is natural left outer join. Yeah, this chapter is the most boring chapter. Well, we have to cover it. Okay, natural left outer join. So join operation can use on condition, or instead it can use natural condition. The same tables are given, and in the previous slide, let's delete everything. We used the on condition, and in the next slide we have natural condition. So what's the difference? When you use on condition, it doesn't matter. The two tables have different attribute names. As long as we specify what attributes should be compared for join, we are good. But when you use natural join condition, two tables must have the same attribute names. Okay, and the same attribute will appear only once in the final output table. Okay, and this natural left outer join has a symbol in relational algebra. We put this parallel line on the left side of natural join ribbon symbol, just like this. And here we are doing right outer join using on condition. Since we are using on condition, attribute names don't have to be the same. And here, since this is right outer join, we need to check what records are not matched. 5 is not matched with any record of student table, but still the 5 should be inserted into the output table, and for the missing attributes we put null values. And instead of on, when the two tables have the same names, we can use natural join condition. In that case, the same attribute will appear only once, and we use this, we put this parallel line on the right side of the ribbon symbol in relational algebra. Next one, full outer join. Full outer join operation stores any unmatched record from left and right tables. So Bob is missing on the right table, David is also missing on the right table, and 5 is missing on the left table. They are all included in the output table. And we can also use natural join condition. In that case, we put parallel lines on both sides of ribbon symbol. Any questions so far? Trivial, right? So, summary. So, up to the previous chapter, what we learned is inner join. Inner join doesn't care about unmatched records. only matched records should be stored in the output table. That is inner join. And we just learned 3 outer join operations. Unmatched record from left table is included in left outer join, and right full I just explained. And we learned 3 different ways of specifying join condition. When you put natural keyword before join operator, we find the common attribute names and use that attribute for join. And instead of using the names, you can use a predicate for join condition. In that case, you use on operator. And if the 2 tables, left and right tables, have the same names, but you want to specify what attribute should be used and what same attribute should not be used in the join condition, then you can use using join condition. And when you want to use multiple attributes for join condition, you need parentheses and list of attribute names separated by comma. I guess we need to stop after this example. So it seems I'm repeating too much. Bio 301, CS 109, CS 109. Robotics is missing on the right side, and 347 is missing on the left side, and inner join will insert only matched record, and left outer join will insert robotics, but not CS347. And again, the same example. When you use right outer join, unmatched records from right table will be inserted. And when you use full outer join, robotics and 347, both will be inserted in the output table. Right, and next topic is view, but we are running out of time. Is that right? Oh, we have 4 more minutes. Let me check. I guess I need more than 4 minutes to cover view. Okay, let's stop here.